Exactflat for SolidWorks. In this example, we have an inflatable boat, a Zodiac type boat in this example, which was modeled from scratch using SolidWorks 3D drawing tools that we are going to flatten in Exactflat. And we've done a little bit of pre-processing work here. As you can see, we've already got our initial flat pattern, which for the developable surfaces should be fine. But we're going to go ahead through the process and optimize this. We've got about 15 pieces here, and as we click on a remesher, we're going to get varying stages of completion for the meshing process. For those who are not familiar with the meshing process, the program creates an analysis mesh, which is optimized for our Exactflat 3D to 2D flattening algorithms. The meshing process is designed to reduce solve time and increase pattern accuracy. And you can see here that we're going to go through these individually. So as the individual pattern pieces are completed in terms of remeshing, we are then starting the optimizer on each individual one. We've got a couple of complicated pieces. You can see there's one that is still remeshing at a 1% level. But for those that are 100% complete, we'll just go ahead and start the optimization. And you have a choice of letting the remeshing process run to completion for all the pieces and then optimizing the pattern geometry of the flattened pieces all at the same time. Or as we're doing here, you can do it as the pieces become available from the remeshing algorithm. It depends on the complexity. So you can see here this piece is a little bit more complex. It's got some strain and sag, but as we start the optimizer, it quickly eliminates those and gives us a pattern piece which is pretty close to the approximate pattern piece that we're going to have at the finish. And I think this one's going to work for a little bit longer because I do see some strain and sag that is residual in there. But the the process is pretty straightforward. Our algorithms are searching for strain and searching for sag. Where it finds sag, it's going to pinch it away, and where it finds strain, it's going to relax it. It does it by iterative optimization. So when a candidate for a flat pattern is presented, it runs the analysis algorithms on those patterns, and when it runs through, it will alter the map of strain and sag. As you can see, it's doing for this piece right here, where there's some sag around the perimeter edges and strain in the middle, and then it'll try and eliminate it, and then it will take a new candidate, which was the results for the subsequent one, and run through the process again. Here, what we're going to use for these ones, these are a little bit more complicated geometry. You can see on the left there's quite a bit of sag and quite a bit of strain, which is to be expected on parts like this. We're going to run a pelt algorithm, which is a pre-processing algorithm. The standard algorithm that runs as a fracture algorithm, we call it fracture, just takes the polygonal mesh, breaks it apart, lays it flat, sews it up where there's gaps. The pelt algorithm literally slices it open and kind of unrolls it. And it's a pre-processing algorithm that gives a different starting point or a different initial candidate for a flat pattern. And you can see it kind of showed not responding there because it was doing some pretty intensive calculations. But once the pelt algorithm is completed, its process, we just run our standard optimizer. And you can see it's making pretty quick work of the sag portions of this at least. And this one will need to run for a little bit longer in order to get an optimized piece. We're about 23, 24% at this point. And it should take a couple of minutes or so to get to the final piece that's, you know, as strain free as that geometry can get without making some relief cuts or darts or something like that. So the easy pieces have already been solved, and the more difficult pieces now are in the process of being solved. This will go much faster if you have a fast computer. This computer we're doing the video demonstration on is not particularly fast. It's a 4-core Xeon processor. If you've got 8 or 12 core machines, our algorithms do support multi-threading, so these things can be done, or the bulk of the calculations can be done simultaneously. And as we cycle through these pieces, you can see that we're about 4 minutes, just over 4 minutes in. We've got the bulk of the pieces done, about halfway done in the other pieces, and we'll just check in on some of these other ones here, see how they're doing. It's getting pretty close. I can see some perimeter edges that need to be sorted out with some sag and some strain. We'll check in on some of the other pieces here. So this particular one, you might actually have to add some relief cuts to get an optimal shape, or it might require some stretch. So for an inflatable, it may be designed to be under some tension, and therefore that's really not a problem. The kind of strain that we saw there, this piece is actually coming along quite nicely, about 91%. And I think for the purposes of this, we may cut the solving process a little bit short. Just gives you a flavor. Yeah, we'll just go ahead and stop it here. It gives you a flavor for how the more complicated geometry can be solved in conjunction with a very simple geometry. Now, I will point out that all these pattern perimeter edges that are mated to other edges or adjacent pieces, those edges, the seam length has to be maintained. So there are some constraints in running this, but this gives you a flavor for how you take a product like this, and this might apply to evacuation slides, lifting devices, any sort of inflatable product out there. It's Exactflat for SolidWorks. If you want to know more, give us a call or visit our website.